Today I am going to discuss the push-pull amplifier. Now what is the meaning of push-pull? Look. When some part of the circuit is active, then that is, its output is going to high, then we say that the output has been pushed to high. And now after some time, if another part of the circuit is activated and the output goes to 0, then we say that output has been pulled to 0 or low. That is the meaning of push-pull. Okay? Now this is the primary of the transformer. This is the primary of the transformer P1, P2. And there is an iron core that the coil is wound over the iron. This one is the secondary. Now at the end of the secondary there will be the signals which are the out of phase, because the transformer, the secondary of the transformer, it is a phase splitter, and one part of the signal is applied to one transistor, the base of one transistor, and other part of the signal is also applied to the base of the second transistor. Emitter of the both transistors are connected together, the NPN transistor, and then the grounded. And at the collector is attached, collector of both the transistors are attached with the primary of the output transformer. And the supply to the transistors given through VCC, and output is taken across the secondary of the transformer where RL is attached. Now the current flows anti-clockwise here, IC1 through transistor T1 and clockwise through the transistor T2. This is the positive part of the signal when arrives here, and negative part of the signal arrives at the lower transistor. Here the signal is coming, input signal. Signal is arriving at the primary of the transformer, and because of the mutual induction, the sign comes here for plus minus. And the base of the upper transistor becomes positive. If the base is positive, the transistor T1 works and gives the current as shown, and the lower transistor at that time remains off because the base is at the negative, because base is P is negative, the lower transistor is off, upper transistor is high. And for the another cycle, this is the current when the upper is high, and at the same time the lower transistor is off. So when the other part of the signal comes, what happens? The lower transistor, the positive comes at the base of the lower transistor, and then the lower transistor becomes high and the current starts flowing clockwise IC2, and at that time the upper transistor becomes off. So this is exactly class B operation. So the transistor is working for one cycle, this exact class B operation, because there is no current flowing in the absence of the signals. So let we write IC1. It is the sum of the DC current plus the AC currents with the harmonics, like 2 omega, 3 omega, they are the harmonics. They are mixed in the signals. Now, for its complete explanation, you go to my previous video, Harmonic Distortions. Now, as the second current is there, but it is out of phase means pi degree, it is leading to the IC1 of every harmonic is leading by pi because of the phase change of pi. Now here we are thinking that this is a general equation. If some DC current, collector current also flowing, if it is exactly class B operation, then there will not be any I naught. Then there will be only the signal currents like omega, 2 omega, 3 omega. But here I naught is also considered if we are thinking that some current is also flowing in the absence of the signals. So because IC1 and IC2 flows in opposite directions, therefore output transformers through the output currents I naught in the secondary of so the transformer will be proportional to the difference of the two currents because the currents are flowing in opposite directions. So we are having I naught equals to constant and IC1 minus IC2. So upon subtraction, substituting the value of IC1 and IC2, we got that omega t, 3 omega t, 5 omega t, 7 omega t, all the odd harmonics are present now. Even harmonics are missed. So that is the advantages of the push-pull connections, that the even harmonics are eliminated. There is no 2 omega, 4 omega now. Okay, this will happen if the two transistors are identical. Keep in mind this thing also. The two transistors should be identical. You know, actually, the collector current consists of the signal frequency and the higher harmonics are always present, but push-pull connections eliminates the even harmonics. So this is very important. Now again, class B push-pull, the better arrangement is, the better circuit is as shown below. Push-pull, class A push-pull is rarely used because of low efficiency. To increase the efficiency as well as the output power, class B push-pull amplifier is used because as for efficiency it is very good, and as well as for the high output powers. When no signal is applied to class B push-pull, then the collector current will be zero. There is no dissipation of the power in the absence of the signal. And dissipation of the power increases with the increased input signals. You know, as well, the average current in class B operation is less than that in class A operation. For detail, you go to my previous videos for class A, class B amplifiers. Hence, power dissipation by the transistor is also less in class B operation. Now, this is the circuit diagram for the class B amplifier. Here we are using the PNP transistor. This is very important. We are using here PNP transistor. Of course, you can make the connection with NPN also. But battery placing should be proper, as shown in the figure. There are the register R2, R1 for the biasings. The biasing is given that for some current flow in the absence of the signal, some of very small current flows. This explanation is given above, how that it is push and pull. One is active and other is off, then other is active, then first is off. Push pull. So the same as the writing is. Like if the base is positive, this is PNP, so the lower will be at lower, the base is negative. So it is good for the lower transistor, current flows to the lower Ic2. Then when the Ic2 flows, then if for class B operation, the upper transistor remains off. Upper transistor is not on. If the lower is on, then, and when the upper works, the current flow Ic1, and then the lower becomes off. So each transistor works for one cycle, for one part of the cycle. You know, transistor generates a large harmonic contents like omega 2, omega 3, omega, but the push-pull connections cancels the even harmonics. So this is very good. This is the signal. Signal is varying like this. Now here there is a problem because for some part there is no collector current for some part. So therefore, the signal there come in the output signal there come a distortion. So sorry, now this is correct. So this is the distortion here. Some part of the signal is missed in the output. So this it is happened for the exact class B operation. And this is called crossover distortion. It is always present in the exact class B operation. Now, how the problem is overcome? This is again a question. And the situation can be improved by the use of small forward biasing to the transistors as indicated, not below, above, that the some base current always flows very, very small, even in the absence of the signal, to eliminate the crossover distortions. And it is shown here in this figure, as well as it is, in the above circuit, the biasing which was applied to R1 and R2, it was because some small base current to flow even in the absence of signal. Then what happens? Look exactly for the input signal how the output will appear now. So there are some base current IB1 and IB2. So collector current is now not exactly 0 for some time. So it is good, like it is advantage. There is no crossover distortion appearing now. There is no crossover distortion. Okay, this is IB2. So it happens because of the presence of some base currents. So crossover distortions are eliminated. That's very, very good. So small current is present in the transistor all the times. The operation is not exactly class B, it is approximately class B now. The bias is provided R1, R2 in the push-pull circuit, like here. Now we're coming to the efficiency of push-pull amplifier. Okay. The characteristics curves, and above is this load line of one transistor above, and below is the load line of the second transistor. Load line of T1 and below is the load line of T2. So this is for second transistor. The I max. Here we find the slope. Slope is perpendicular over base. And we take the inverse of R dash is the exact load which is VCC over I max and equals to N1 over N2 whole square into R. R dash is the load. So output swing is a fraction of the Now lastly we are coming to the efficiency, output power of the DC power, and it comes out equals to pi k upon 4. Now substituting the values, if we think that the maximum efficiency, then k equals to 1, it comes out 8.5%. Very good efficiency